presentation by Dr. Brian Swingle from Harvard University. His title is RG Construction of Quantum State, or as sorcery. Okay, that's welcome.
Thank you. Yeah, thanks very much for the invitation to come. It's my first time in Taiwan, so I'm having a great time so far. It's been a great workshop. So over the next day, today and tomorrow, I'm going to tell you about an approach we've been working on to construct, that is, literally build quantum states of many body systems in terms of some sequence of unitary transformations from product states. So this talk will be very focused on the state. There will not be any Euclidean field theories or anything like that. Very focused on the state, heavily influenced by quantum information ideas. And yeah, you'll sort of understand this as sorcery, hopefully, a little bit later. And I should mention also that my chief collaborators in this work are first John McGreevy, who's a professor at UC San Diego, and then Sheng Long, who's a postdoc there. Sheng Long enters the story a little later on. The early work was done with John. And I'm actually now at Stanford, but I was at Harvard while some of this was done, so.
Sorry.
No, that's fine. I just, so yeah. So here are just the references. There's really only one reference, although this builds upon many years of work. There's a 90-page paper, you can read it here if you want, with John, where we define this S-source framework and investigate gapped phases. And then coming soon, I hope, within a month, I think, maybe less, will be a paper talking about certain infinite class of gapless states, which we call square root states, which I'll explain what that is a little later on. And then there's other work in progress with various people, which I won't really talk about. And I just want to also mention that a very important precursor work, which you'll perhaps see the influence of, is Vidal's idea of Mira, and also other tensor network approaches that Xiaogang and Frank Verstrada and various other people have worked on very extensively. And just direct you to this paper. There's a very long bibliography where you can find lots of references. So here's the overall picture of what we're going to do. Part 1 and 2 we'll do today. So in the first part, I'll introduce sort of the fundamental goal that we want to achieve and some basic notions, and I'll define the idea of S-source RG. And then part 2 is I'll talk about the application to gap states. So this part 1 will be mostly before lunch and part 2 after lunch. And then 3 and 4 I'll talk about application to gapless states, these particular square root states, which I'll define tomorrow. And then finally, conjectures, connections, and what we're going to do next in this program. Okay, so let's get started with the basic goals. So here's the overview. I'm going to define what I call the ground state problem, and this idea of Hamiltonian motif, and some other terminology. Then I'm going to tell you the scope of the work, and then I'll start with a few examples and then give you a formal definition of what an S-source RG fixed point is, and then I'll discuss briefly some properties of this fixed point structure. So here's the ground state problem. Since this is a whole conference on topological order, I don't think I need to emphasize too much. The physical picture is that we can cool systems down very low temperatures, much below the characteristic scale. So the ground state is an interesting object in that context. And we can kind of formalize this problem as saying it's a task. You give me a Hamiltonian, I'm supposed to give you the ground state, or at least to calculate physically measurable quantities like magnetization or entropy or whatever. And the question I want to ask is, first of all, you should notice this determine is in quotation marks, and that is meant to scare you, because the wave function is we're taught in graduate school, is a 2 to the n dimensional vector. So it's impossible to write all those numbers down. If you fill up the Hubble volume of the whole universe with the best storage material you have, you could store the state of 300 spins. So somehow the wave function as a giant vector is a very fake thing that we never think about, really. So what we really mean by determine is some more useful or efficient, a better way to set, to name the wave function, to give it a specification. And so the question that can inform all of my talks is, is there any way that there could be a general algorithm or procedure to solve this problem, where I give you a Hamiltonian, you don't know anything, maybe it's local, that's all you know, and you're supposed to tell me what is its ground state. And of course, that sounds very hard, and in fact, it's provably impossible. So, for example, Gottesman et al. Showed that you can encode the solution to very hard quantum mechanics problems. A problem which is hard even for a quantum computer as the ground state wave function. So there's no way that you can have a general algorithm to determine the ground state. On the other hand, the kinds of states that these people were talking about to prove such a theorem are very, very pathological from the point of view of ordinary condensed matter physics. So it's not clear that there is not a very large class of systems for which you could have, in principle, a very general method to figure out what the ground state is. And so what I hope to convince you by the end of tomorrow is that for a very, very large class of Hamiltonians, the answer is actually yes, there is a general procedure, there is a general framework which would enable you to figure out what the ground state wave function is and to compute physical properties. Okay. Now, briefly, what I mean by a Hamiltonian motif. This actually came up in conversation at dinner last night, but I said here Hamiltonian, but as physicists we know that we really care about families of Hamiltonians, right? We don't just want to care about, a chunk of carbon which is 1 centimeter by 1 centimeter. We want to care about, carbon of any size, right? They're all sort of the same thing to some extent, modulo boundary effects. So really what we have in mind are families of Hamiltonians, like Hamiltonians, like a sequence of Hamiltonians on different size systems, for example, to define a thermodynamic limit. And so one way you could try to formalize this is with the idea of a Hamiltonian motif, which like Hamiltonian pattern, which you could think of as like a function from graphs to Hamiltonian. So you put in a graph and it gives you out the Hamiltonian on that graph. So for example, you could think about the Ising model. You put in a graph, and for every edge in the graph you do a ZZ, and for every vertex you do an X, and that's the transverse field.
Is graph a lattice here?
It's just a graph. I could restrict to lattices. If I want. Yeah.
So in the Ising model, what is in the Ising model is the graph?
I'm saying what we mean by the Ising model is like you tell me I'll tell you the Ising model on the triangular lattice, or I tell you that's what I mean. So you insert triangular lattice into this function and it spits out the Hamiltonian.
Oh, so the graph G is a triangular lattice.
Yeah, exactly. So I'm just trying to give a sort of more mathematical sense of what we mean is like there's some rule, like for every link you put a ZZ. There's a pattern that you fill out your graph with, whatever it is. And that's what we mean by the Ising model, in essence.
But for more than three body and more interaction, you need to define general.
Some simplex or some more general object. Yeah, that's fine. So it's just a way of taking some geometrical data, let's say, and assigning to it a Hamiltonian. But I don't need the full power of this idea. What I really want to consider is just what I'll consider throughout these talks are families of Hamiltonians indexed by system size. So the Ising model in a square lattice with periodic boundary conditions of size 1, 2, 3, 4, and so on. So this family of Hamiltonians. And there's going to be a corresponding family of ground states, or possibly degenerate ground state manifolds, which depend on system size, potentially. And because entanglement will play such a crucial role, what we're always going to allow ourselves to do is, at any step in the game, we're going to always allow to add or remove product states at will. So we can add unentangled degrees of freedom. That's sort of free, because those are not participating in the many-body dynamics. And so what we'll actually do is we'll try to relate wave functions of some size, L, to wave functions of a larger size, using product states to fill in the extra degrees of freedom and then doing some local operation. And just as for the scope, most people here have spoken about gap states, and we will talk about those first today, but we'll also talk about gapless states. And I just want to emphasize that the framework is very general. We believe it encompasses a very large variety of phases of matter, including, for example, Fermi surfaces. And so yeah, it's quite general, and so I emphasize we're talking about dynamics here and not just the properties of some deep infrared fixed point. So I want to solve a real Hamiltonian. And the conceptual tool that we're going to use is the renormalization. Okay, so here's kind of I'm going to have a 2-slide cartoon review of your normalization group. So you imagine you have your Lagrangian, or your Hamiltonian if you're a condensed matter person. And as a function of the length scale system, so there's a UV defined, here's the UV up here, with at short distances at the lattice scale, there's some UV Hamiltonian, which you specify. And then as you look at longer and longer distances, the effective Hamiltonian flows in coupling constant space, right? So you have, for example, start here, this is your microscopic Hamiltonian, and you flow down towards this fixed point as you look at longer and longer scales. And the coupling constants flow according to this beta function. And an interesting feature of this beta function is that it's local in scale, so it only depends on the couplings at the same scale to calculate the couplings at the next scale. And what's nice about this picture is that it gives you a very simple visualization of phase and phase transitions, right? So everything in the blue here corresponds to phase 1 because it all flows into this point, right? So why is everything in the phase the same in terms of its universal properties? Because it all flows to this one point in coupling constant space. So this controls the physics. And over here, you're flowing somewhere else. That's phase 2. And then this dashed line right here separates the two. That corresponds to the phase transition. So if you're exactly on this line, you flow to the critical point. If you're a little bit off, you flow close, but then you flow to here or to the other phase. And now the key idea that we're going to pursue is sort of to try to think about the state of the system at some arbitrary microscopic point here in terms of what it looks like sort of along this flow. So we decompose the state in terms of its different energy scales along this flow, and then we sort of put everything back together again to construct the full wave function. So you'll see in a moment much more precisely what I mean by this, but that's kind of the broad, sweeping picture of what we're going to do. We're going to decompose, in fact, the entanglement in the system, scale by scale. And that's how we're going to think about the ground state function. And so, just a note on terminology, based on the workshop title, I feel that I can use all 3 languages with impunity, but please ask if something's unclear, because I can't keep straight in my head, if it's gap or mass or whatever, so just ask. So here's precisely what we're going to try to do. We want to have a wave function. In fact, we have this family of wave functions of states, indexed by system size. And we want to relate them to product states. That's here. So 0 to the L is the number of sites. Think about one-dimensional system with some unitary transformation. Right, so this is in principle an experimental procedure. If you had a quantum computer, you could actually build this state from product states using this unitary transformation. And I want to emphasize this U is not going to be finite depth circuit. In fact, it'll typically be logarithmic depth. But it will have some kind of renormalization group structure. And the way that we're going to make this U is what we call the S-source RG framework. Okay, so this is what we're aiming for. So here's kind of the first most trivial example that you can have. So let's imagine you have a system and particles in one dimension. There's no interactions. There's one particle per unit cell. And a particle can hop, but there's alternating weak and strong bonds. So this is an insulator. It has 2 bands. One of the bands is filled. The other band is empty, and then there's a gap. It's an insulating state. It has an energy gap. And we sort of know in our, deep in our core that this state is kind of trivial for an obvious reason, which is that you can deform the weak bonds to 0 without changing the physics, and then it's manifestly just decoupled systems. So there's some precise sense in which this insulating state is more or less just a bunch of decoupled 2-site systems. And so what we'd like to do is actually construct a unitary transformation which takes the state of this system to the state of this system. And the reason why we call it S equals 0 is because, so this S stands for the number, the amount of sort of entanglement you need to create the wave function. So here we can create the wave function at any size. I can make this chain as long as I want. I can create the wave function at any size from product states. So I don't need any raw materials. I can just start from product states and I can make the entire wave function in one step with essentially a local unitary transformation. So this is sort of the most trivial case you can consider. Here's a more interesting case. This is a one-dimensional example where we'll have S equal to 1. And I'll define S just in a moment. So in this setting, what would happen is you'd have L sites which carry some non-trivial state. So that's these black dots here. They carry some non-trivial quantum state, which is here denoted as psi sub L. I interleave with these black sites some blue sites. So I just put them in between like that. These blue sites are initially taken to be unentangled, so they're just in their product state. And then the rules of the game are that I'm allowed to mix the black and the blue using a local unitary transformation, which means local with respect to the geometrical distance on this lattice. And if, with some local unitary, which is here the red U, I can produce the wave function on 2L sites, then I say that psi L and psi 2L form, this sequence is an S equal to 1 fixed point. So if I can make the wave function on twice the system size from the wave function on half the system size, plus a bunch of product states with a local unitary transformation, then we say it's S equal to 1. And again, S refers to the number of copies, the number of copies of this state I need, which is just 1 in this case. So here's the definition. A d-dimensional S-source fixed point is a system where a ground state on twice the system size can be constructed from S copies of the ground state on system size L plus extra unentangled degrees of freedom using a quasi-local unitary transformation. So here's the picture in 2 dimensions now. The black sites contain my non-trivial wave function. The blue sites are product states. And I'm allowed to mix them up with some local unitary. And what has to come out is the black state on twice as many sites. So this is S equals 1. But if you could, in principle, imagine a system where you need not 1 copy, but 2 copies, for example. And that would be S equals to 2. But today, we're not going to talk anything about S greater than 1. Tomorrow, we'll talk a little bit about systems with S greater than 1. And we kind of conjecture, and you'll see this as a reasonable conjecture, that this structure is sufficiently general to essentially encompass every state of matter you've ever thought about. That's kind of the claim. Okay, and now let me just make a technical point. What this quasi-locality means, so Xiaogang talked about circuit definition where you allow some finite depth quantum circuit. So this is a slight generalization of that notion where I don't have a quantum circuit, I actually have a local Hamiltonian that evolved in time. And moreover, I allow this Hamiltonian to have a slightly, it doesn't have to be strictly local, it can be, have a rapidly decaying sort of almost exponential tail. And so what I mean by a quasi-local unitary U is quasi-local if it's e to the ik, where k is quasi-local. What does k quasi-local mean? It means k can be written as a sum of terms, k sub x. Each of these terms themselves can be decomposed into strictly local operators that live inside disks of radius r centered at site x. So it's a sum of operators on bigger and bigger disks. And that's what this statement here is, that the support of this operator is contained in this disk, with the additional proviso that the operator norm decays sufficiently rapidly with the disk radius. So this is not actually exponential decay, and you'll see why we can't quite do exponential decay, but it's more or less, think about decaying exponentially. So it's a sum of local terms. Each local term is localized at some point with a tail which decays faster than any power of R. Okay. So now let's talk about briefly some properties of this thing. And so the first property that's interesting to look at is the entropy of a subregion. So imagine you have a large system now, and you look at some subregion, which I've called here A, and you can take the state of the whole system, you can trace out its environment, right? So let me draw a picture here. You have a large system. Here's A. Here's the complement. Rho A is obtained by tracing over A bar of the quantum state of the whole system. And I want to calculate the entropy, this thing, of this subregion. And now what we can show using the definition of the S source RG is that there are bounds, recursive bounds on the entropy. So the entropy of a region twice the size has to be less than or equal to S times the entropy of the original region, plus a term which scales as the boundary of that region. So here's the picture of that. Let's first think about the case of S equal to 0. Then there are no initial copies. So I have this thing, and I have a bunch of product states. I can mix them up with a local unitary, but intuitively that local unitary transformation can't create entanglement between this region and this region. It can't create entanglement between distant objects. It's only a local transformation. So it can only create entanglement sort of across the boundary. Right? So if I start with a product state, all only thing I can get is area law entanglement, and that's what this bit here tells me. But if I initially have some copies to begin with, right? So if I'm in here now and I have some copies, so let's say like this. Well, now you see there could be some pre-existing entanglement between the black sites. And there could be entanglement between black sites deep inside. I don't rule that out. But there's no entanglement from the blue sites. But I can still add a little bit of extra entanglement from this quasi-local unitary transformation. So what it's saying is I have a region of size R, and then I put a bunch of them together to make a region of size 2R plus some extra unentangled degrees of freedom. So the total entropy of size 2R has to be less than the entropy of size R times the number of copies of size R plus any extra entropy I can get from the local unitary transformation. So that's the way that this entropy bound works. And so actually you can use this entropy bound to prove that if S is less than a certain number which depends on the dimension, then the system obeys an area law.
What is K and K prime again?
K and K prime are just constants that depend on the unitary. So they depend on the details, but they don't depend on system size.
So this is only for ground state or for generic?
Well, so as I phrase it here, this is true for any S source fixed point. So any set of wave functions with this property that you can relate them, you know, L to 2L in this way, then the entropy obeys this bound. Now, what I'll claim later is that essentially this captures well different kinds of ground states, whereas a highly excited state may not have this structure. And actually, similarly, there's a lower bound. The entropy also can't be less than the entropy of the original system times S minus some area law amount. So you can actually use this to prove that if S is too large, if you have too many copies going in, the entropy has to actually violate the area law. So there's actually a bound, there's a separation, where S is 2 to the D minus 1, D is the spatial dimension. So below this it's area, above this it's super area, and here it's area log area. This is the entropy. So we'll talk more about this tomorrow, but for now.
There's a question. If for the S bigger than 1, for example, whether the construct state have a natural local Hamiltonian as a negative 1 state?
Yeah, so in this, just as I define it here, there's no guarantee that that's true. But if as I'll show later, it is, I mean, if each of these psi L's are themselves the ground state of some local Hamiltonian,
Okay.
then, so it's a more general construction than that. But
So if each copy is a ground state local Hamiltonian, then the after renormalization is still ground state.
yeah, exactly.
Okay,
Yeah.
that's good enough.
Yeah. So I want to mention one other thing, which is the ground state degeneracy. That's also an interesting, very interesting object. So here, let's just think about this, having some system defined on a square lattice of some linear size L. So then we can ask what is the ground state degeneracy, as a function of system size L. So for a trivial state like that dimerized insulator, the ground state degeneracy is just 1. There's only a single ground state. For a topological state, it's some fixed number, depending on the topology of the manifold, but it doesn't depend on system size. However, you can easily show that for an S-source RG fixed point, the ground state degeneracy at size L and the degeneracy at size 2L are related by this formula. And that just means that you have S copies at size L. Each of them has their own degenerate ground state manifold. You can pick any of those ground states and mix them together. Because the unitary transformation is local, it doesn't care which ground state you pick. So the ground state degeneracy actually has to grow with system size if S is bigger than 1. So this immediately tells you that S equal to 1 or less is what has to describe topological things as we normally conceive of them. And if you have S more than 1, then you have a very strange structure where the ground state degeneracy depends on system size in some particular way. And there are such examples, some trivial, some not so trivial, and we'll talk about them tomorrow.
So you're not assuming you're changing the topology as you...
Yeah, well, in this case, I'm just imagining like torus, just let's take a torus, or any other system that you just expand uniformly. So it could even be a sphere if you wanted. But let's say a torus for simplicity.
But have you considered like you could actually wrap up and then glue the boundary? And you could also do that by local unitary at the boundary.
So say it again, if you wrap in...
Suppose you are on this plane and then you glue the boundary, the boundary become a torus, then the degeneracy may change.
Yeah, but that would usually involve some gapless somewhere in the...
Okay.
Yeah. So in that case, we wouldn't expect that this actually is a fixed point in that case, because you're doing something global. Okay, so the point of this framework so far is that it has a very nice structure in terms of entropy and ground state degeneracy. It gives a very nice way to calculate the wave function. And I want to emphasize what's meant by nice is that it's very efficient both quantum and classically to make it work with this state. So if you have a quantum computer, then you can actually construct the wave function with a logarithmic depth circuit, which is an extremely efficient circuit. And if you have a classical computer, then you can calculate expectation values of local observables in time which is polynomial in some relevant parameter, and independent of system size, or at worst logarithmic in system size. So this means whenever the wave function has this representation, then I can calculate physical quantities, at least certain kinds of physical quantities, very efficiently, even on a classical computer. And what I mean by mundane obstacles here are just that the existing algorithms are very complicated. They're polynomial, but they have a high polynomial cost, so they don't work very well. But one of the messages of this talk will be that this framework seems to be correct to describe ground states, and so we should probably work much harder to devise intelligent ways to take advantage of this structure to actually calculate physical quantities. So for example, we can prove that you can calculate local expectations in fraction quantum Hall states in time log and system size, which is doubly exponentially faster than the best available quantum Monte Carlo algorithm. So we just proved that you have, for large enough system size, this method will always work, infinitely better than some existing, Monte Carlo, for example. So therefore, there's really, motivation to push hard on this, I think. And although I won't talk about it at all, this methodology, this technique also can give you more traditional tensor network representations. So PEPs, matrix product state, MERA, all this kind of stuff. I'm not going to talk about, but you can actually get it from this framework. Okay, so that's part one. And the overall message is just that we have this framework, which is essentially relating wave function at different system size to each other using local transformations. This framework has nice properties in terms of its entropy, and it's computationally useful. So if you can show that a wave function has such a structure, then you could actually calculate with it, in principle, at least on a computer. So now what I want